So in the first couple of lectures of this course, we introduce this area of parameterized complexity. And so basically in the parameterized complexity, if you recall the kind of problems, for example, in the vertex cover problem, we had input g comma k, and then we had a question, and question was, does G has a vertex cover of size at most k, and our parameter was k. So basically all we are trying to do is to design an algorithm where the running time dependence is only on my parameter, and the other dependence on the input size is just polynomial. That's all that we should care about from now onwards. So your problem will have three pieces of information: an input, a question, and the parameter. And the parameter should tell you that you need to design an algorithm such that the running time is like f of k and polynomial in the input size, and this f of k could be any function which depends on k only. Okay, so that's with that in mind, let's try to learn our first set of tools. These set of tools are very basic, and these are called kernelization or polynomial time preprocessing. So the first technique that we are going to learn is called kernelization and polynomial time preprocessing, or rather this is also called or polynomial time preprocessing. Okay. So it's a standalone technique and it has its own merits, and we will see how to. Okay. So the plan of the lecture is very simple. The plan is that to define you what kernel is, give you some simple examples, and tell you how FPT and fixed parameter tractability and kernelization are related, and give you a couple of more examples in the next two lectures. Okay. So let's just get started. So what is kernelization? So basically it's like, in philosophically you can think of this, that every block of stone has a statue inside it, and it is the task of the sculptor to discover it. So there's a big problem, but not every aspect of the problem is hard. It's just our job to get rid of all the easy things and get to the hard nut or the difficult problem. So with that philosophical quote, let's just get started. Here's a simple preprocessing that you see quite naturally in day-to-day life, is that if you play Sudoku, where in Sudoku, if you recall, that it's like a 3x3 block Sudoku. So in every 3x3 boxes, you need to have numbers from 1 to 9. Every row has to have a numbers from 1 to 9. Every column has to have a numbers from 1 to 9. And suppose this is a partially filled Sudoku table. Now notice that here, by looking at this, we can fill 1 by what is called cross-hatching preprocessing. Why? Because let's look at 1. So because 1 is present, because 1 is being present, 1 is present here, right? That implies that 1 cannot be in this row. Okay. Now notice that 1 is present here, so it implies that 1 cannot be in this column. Now 1 is also present here, so it implies 1 cannot be in this column. So, but we know that in this box we need to fill 1. So by applying some simple rule, we are able to determine that actually 1 needs to be here. Okay. Similarly, we can say about let's say 9 here. Okay. Similarly, we can say about 9 here, if you notice 9, right? Why? Because look at this box, presence of a 9 here, rules out 9 in this column, presence of a 9 here rules out 9 in this row, and presence of a 9 in the last column rules out. So then if I look at this, then the only entry which is left to be filled with 9 is here. So these are called cross-processing rules. So notice, given an instance, you are able to determine some reduction rule which tells you where to look for the new value. Okay. So, this kind of pre-processing is quite ubiquitous in actually in computer science. Okay. So, lots of if you look at linear programming solvers like Simplex and everything, they rely on such kind of simple rules to reduce your data. Okay. Navigation systems, microarray data analysis for classification of cancer types, and so on and so forth. So this kind of polynomial time preprocessing to reduce input is quite well present in every aspect of computer science and science in general. Okay. But what we are interested in is like in terms of analysis of algorithms, like some naive question. So, now suppose I take my favorite NP hard problem, okay, and I ask, is there a pre-processing algorithm which is a polynomial time algorithm that guarantees to reduce every instance of problem, say, by 5%. So, let us see what happens if we had such an algorithm. So, what I am saying, so for example, look at example of our vertex cover. Let us look at the example of a vertex cover problem. So, suppose I had an algorithm, here is an algorithm for say the black box, which is a vertex cover. For vertex cover, it takes an instance g comma k, okay. It outputs an instance g prime k prime, okay. Okay. And what is more a specification of this? It is a polynomial time algorithm. Okay. Okay. And what more, g comma k and g prime k prime are equivalent instance. So, let us, what is the meaning of this? Meaning of this, if you started with g comma k, which is a yes instance, then g prime k prime is also a yes instance. That is, g has a vertex cover of size k, implies g prime k prime has a vertex cover of size k. If you started with a no instance of vertex cover, g does not have a vertex cover of size k, then the reduced instance g prime k prime also does not have a vertex cover of size k. So, in other words, in mathematical you can say equivalent can be well defined as follows: g has a vertex cover of size at most k if and only if g prime has a vertex cover of size at most k, right. So, g has a vertex cover of size at most k if and only if g prime has a vertex cover of size at most k prime. Okay. Now, what is the meaning of this? So, this is an amazing algorithm, that polynomial time algorithm, that takes an instance of a vertex cover, outputs an instance of vertex cover without changing the answer, which is great. Now, what happens if this algorithm reduces, suppose even by 1 bit? Okay. So, let us ask ourselves a simple question. Let me make it small so that you can see everything in one go. Okay. What happens if we are guaranteed that, say, g prime has one less edge, say, or vertices, whatever. Suppose if this is a guarantee this algorithm could do, then what we could do is the following. Okay. Then we can feed this algorithm again and again, and from g prime g k, I will get an equivalent instance g prime k prime dot dot dot. But after poly steps, poly in say n steps, what will I get? I will get some g tilde k tilde, such that the size of is like constant. Right? Now, once this is done, once I have applied this reduction rule or polynomial time algorithm, then if I apply polynomial time algorithm polynomially many times, I still a polynomial time algorithm, but we started with a large instance, but after polynomially many application of this algorithm, we are able to reduce the input size to constant, and now we can solve the problem in polynomial time. That would tell us that that would be a contradiction to our assumption that there is no polytime algorithm for NP-hard problem, right? And that is a reason why it is there is no algorithm that can guarantee to reduce every instance of the problem, say by 5%. In fact, even by 1 bit, it is not possible, because you start with an instance will have polynomially many bits, and if you are able to reduce even 1 bit in one invocation of your algorithm, then after polynomially many application of this algorithm, you would have reduced to the constant size, and then you can solve the problem optimally. Well, yeah, so that is what I meant by strange here. So at first glance, there is no interesting theory for preprocessing of hard problems, and we will see how the kind of algorithms we would like to design, this theory naturally comes into play. Okay, so let's take a new problem today. So our new problem is what is called point line cover. So you are given a set P of n points in the plane, an integer k, and I would like to know whether there is just k lines that covers all the points. So look at the set of points given here, look at the set of points given here, and if you notice that I can take these 3 lines and that will cover all the points in the plane. Okay. Okay. Now, so we can also assume that there are at most n square lines. Okay. We can also assume that there are at most n square lines. Why? Because notice that I mean, why do you care about a line just containing 1 point? Because I mean, and why do you care about lines which doesn't touch anything? So it's best that line should contain touch or intersect at least 1 point, and that if there are n points, you know that like there is no point taking a line which contains 1 point, because you could very well take a line which contains at least 2 points, and between any 2 points you can draw a unique line. So we can assume that the space of lines which we should consider is n square lines given by lines passing through 2 points given in the plane. Okay. Okay, so we can assume that there. So my reduction rule is very simple. If there is a line L which cover more than k points, removing all points covered by L and reduce the parameter k by 1. So let's try to understand what is this rule saying, why the rule is sound. Okay. So the reduction rule is very simple. Okay. So the reduction rule is this: if there is a line covering more than k points, which means, okay, so we have to show, so suppose my instance was, sorry, okay, suppose my instance was, this is set of points and line k, okay. Now, what is my instance? So, what I will do, suppose if there is a line L covers which is more than k points, so suppose L covers k plus 1 points, my reduced instance is, let's P minus points covered by L and k minus 1. Okay. Let's try to show why this is sound. Okay. So what is the meaning of sound? So sound, as we have told before, it means, say P comma k is a yes instance if and only if, say this is, let's call this the set of points covered is P prime, comma k is a yes instance. Okay. Let's prove. Okay. Forward direction is trivial. Or which direction is trivial? I think the reverse direction is much more trivial. Right? So why reverse direction is trivial is because, well, if P prime can be covered by k minus 1 lines, then add, if P prime can be covered by k minus 1, then add L to these lines, and then they cover all the points, of P. Okay. Why? Because the only points that P prime does not have belongs to this line L. So, if you could cover all the points of P prime with k minus 1 lines, then you add L, right? Then you add L to the set of the lines which covers the points of P prime. Now, the budget is k minus 1. Now, you have added one more line. So, budget has become k. So, you are only using k lines and you are able to cover all the points. Now, let's okay, but what is the forward direction? This is an interesting direction. Why? What have we done? So, we are essentially saying, so look at this. So, to draw this, just draw some pictures. So, suppose these are my lines, suppose these are my some say dot dot dot, and suppose this is my line which covers this, say, greater or equal to k plus 1 points. Now, ask ourselves, if I do not pick this k plus 1 line, these points are collinear, right? Now, you take any line, any other line, how many points can it cover? If I do not pick this line, any other line can cover at most 1 point, right? So, what does it implies? Implies if we do not select L, then any solution needs at least k plus 1 lines. So, if we are looking for, which implies if we are looking for solution of size at most k, then L must belong to my solution, Okay. Then we are done, because now what happens? Then for the forward direction, we know that there is an optimum solution which contains the line L. So, now which implies that if you take out all the points that L covers, there are k minus 1 lines that cover all the points which L does not cover, and that is precisely the points in P prime, right? Which implies that if, then okay, implies suppose if you had a solution, then L, L1, L2 dot 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 Lk minus 1, right, where L is the hour, then this covers P prime, and we are done, as we are able to cover all the points of P prime with at most k minus 1 lines. Okay. So, we have shown that, well, if you have an yes instance of this, then we can get an yes instance, then P prime is also an yes, P prime comma k prime, k minus 1 is also yes instance, and other way around. Okay. Very okay. So, what happens? So, at each of the steps of the reduction rule, we obtain a problem with a smaller number of points. Thus, we either end up with a problem with no point left. So, if we apply this reduction rule exhaustively, what could happen? That every step we are reducing some number of points and parameter decreases. So, we either end up with a problem with no points left, and in this case we have actually solved all the problem, and then we can say yes, this is an yes instance. Okay. Or the parameter k is 0, but still some points are left. So, like we are applying this reduction rules every time that, okay, look, there is a line which covers so much points. If you do not pick him, then your budget will be large. So, you apply this rule, but you have applied this rule exhaustively, and still there is some points left. then you know that there is no way that we can cover all these points with just k lines. Or we arrive at the problem for which our reduction rule cannot be applied. Okay? What happens? Well, the point is that we are applying this reduction rule. It's possible that this reduction rule doesn't apply, and if this reduction rule does not apply, then let's see what happens. Okay. If the reduced instance no line can cover more than k points, then a reduced yes instance cannot have more than k squared points, right? Correct? So, which implies, what does this imply? This implies very interesting things, right? So, when you know that, like, if every line covers only at most k points, then k line together can cover at most k squared points. So, at this point of time, we can say our reduction rule is if number of points. So, this is why we say, look, yes instance, right? We are able to bound the size of the yes instance. If it is a yes instance, meaning there are k lines that can cover all the points, right? So, in those instances, you know that each line covers at most k points. So, the total number of points that could be present is at most k square. Okay? So, here is a simple thing. What we will do? So, if this is the case and if the number of points are more than k square, then you will say no, this is no instance. So, in polynomial time, we reduce instance p comma k to an equivalent instance p prime k prime such that the size of p prime is bounded by function of the parameter k only. So, this is the difference between parameterized complexity and classical complexity, that in the classical complexity we cannot say that every invocation of the polynomial time algorithm will reduce the instance size. But here we can say that, look, if we cannot reduce the instance size, then I can at least guarantee you that the size of the instance is bounded by a function of k only, or function of the parameter k only. So, parameterized complexity or this field allows you to say a third thing: yes, no, size is bounded. Okay. So, now let us define this notion of kernel formally. So, it is a pre-processing algorithm. It takes an instance I comma k of a problem q. Let me not, okay, of q, and returns an equivalent instance of the problem, and the output size of is a is like, this is size of a is like maximum size you could have in terms of k. So, this is why it is defined formally in terms of supremum, but let us not care about them, because we will see, we will be able to analyze the size of this by hand. So, a kernelization algorithm, or simply a kernel for a parameterized problem q, is an algorithm A that, given an instance iq of q, works in polynomial time and returns an equivalent instance I prime k prime of q. Okay? And we require that the size is bounded by some computable function g, right? Okay? And you will see why we need this, but like, again, computable function just means that there is a Turing machine that, given an integer n, it will work in polynomial time. It will work in time. It will, at the end of this, it will write down g of n in the output table. That's it. Okay, but our functions will be like 2 power k, poly k, something of this nature. So, I would not worry about them. Okay. This is, once you have understood the concept well enough, you can go and start putting these formal notions to make the theory go through the mathematical rigor. Okay. 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 So, now when size of A is polynomial in K, we say that A is a polynomial kernel. Okay. So, for example, what was the size in point line covered? Well, we were able to say that the size of the kernel is like roughly k squared points. Okay. So, we say that A admits a polynomial kernel. Okay. The size of kernel is generally, the way the size of the kernel should mean is bit size. What is the number of bits you need to represent the output instance? But often it is good to specify number of vertices, edges, points, clauses, etc., that you are able to reduce in the smaller instance. Okay. So in that language, what did we prove? PLC admits a polynomial kernel with k squared points. I am not saying k squared bits because each point could require certain amount of representation based on how precisely we are representing. So let's not get into those. All we have been able to do is that point line covered admits a polynomial kernel with k squared points. Okay. Just a minute. Okay. So let's just continue. Okay. So let me give you another example. Okay. This is our favorite problem. A graph G and integer k. Is there a set S of at most k vertices in G so that each edge has an endpoint in S? Now, there are some simple reduction rule for this. Like for example, if you had this vertex, isolated vertex, you never need this isolated vertex because it is not covering any edge. Similarly, if a vertex covers k plus 1 edges, then if you don't pick him, so for example, if I don't pick him, this red vertex, then how many vertex do I need in vertex cover? 1, 2, 3, 4, 5, 6, 7, right? All its neighbors must go into my solution. So if I do not pick a vertex, then there are like 7 neighbors, like all its neighbors must go to the vertex cover because who will cover these edges? Which implies that if there is a vertex of degree strictly greater than k, then this vertex must go into the solution. So again, the reduced instance, you delete vertex v from the graph and you decrease the parameter by 1. You can prove that G is like these reduction rules are sound. It's the way we proved for point line cover because you replace line with a vertex and the argument would go through. Okay. So, and why if G comma k is an irreducible instance that G has at most k square edges? Because look, if a vertex can cover only k edges, then k vertex together can only cover k square edges. So, if every vertex has degree at most k, you are able to get to that stage. And if the number of edges are more than k square, you will immediately say no. So, what we are able to show because of that is that vertex cover admits a kernel with k square edges and k square k plus vertices. Okay. Okay. Why k square plus k vertices? Because look, let me just say, let me just draw some picture for you. So we have reached the stage that we have, if there is a vertex cover of size k, they have degree at most k, right. So the total number of vertices, total number of edges they cover is like k square, that's correct. But total number of vertices could still be k square plus k because this could be stars on k, guys, right. So like this. So they cover k square edges. So these guys, so k square vertices from there and k for themselves. Okay. So you can show just like point line cover that vertex cover admits a kernel with k plus kernel with k square edges and k square plus k vertices. Okay. Okay. So we will do last example for this lecture, which is about edge clique cover. So what is edge clique cover? So input is a graph G, integer parameter k, and we have to decide whether edges of G can be covered by at most k cliques. Okay. So I want to find k cliques so that look at any edge, it participates into one of the cliques. So look at this example here. We have this blue clique, red clique and yellow clique, and look at any edge, it must belong to one of the clique. So for example, this is your graph. So you can just check that every edge belongs to some of the cliques. So the question is, can we partition my vertex set into, or not partition, that's the wrong word, can be find k clicks in my graph such that every edge participates into one of these clicks. And they are not partition or vertex set, because look at the blue click and yellow click, they intersect. Red click and blue click and yellow click, they all intersect. So we just want to find k clicks so that look at any edge, you can at least find one click where this edge belongs to. So we will show that edge clique cover admits a kernel with 2 power k vertices. Okay? So here I have a reduction rule. Delete all vertices of degree 0. Okay? So let's delete all vertices of degree 0 because they are not adjacent to any edges anyway. So first of all, they can't participate into any clique, and even if they participate, so they can't participate into any clique anyway, or except the clique of one vertex. But clique of one vertex covers no edges, so that's redundant. So you can remove them. But look at reduction rule 2. If G contains an edge UV with their close neighborhood to same, then we would like to contract UV. If UV was an isolated edge, decrease k by 1. So what is the meaning of this? Let's look at this. First, what it says is that look at, suppose this is my graph, and here is an edge UV who has an edge among themselves, and they have the same neighborhood. U has the same neighborhood, V has the same, which is this patch. Then I am saying that apply a following reduction rule. What is the following reduction rule? Is let's make the same vertex UV and make them adjacent to, like you just contract UV into a single vertex, and here it is. Okay. So our instance become G comma K, and say, hey, look at G U comma V K, which is contracted. Let's call this. This is what. So contraction means you identify U and V and make all the neighbors, like if a vertex was neighbor to U, you make a neighbor to UV. Okay, that's it. And so like anyway they have a common neighborhood, so like doesn't matter. Okay. So now I want to say that, well, this reduction rule is safe. What is the meaning of reduction rule is safe? So look at the forward direction. Suppose C1, C2, Ck are k clicks. Okay. Now, what could happen? This clique could contain U, but maybe or this clique could contain V, or this clique could contain UV. What I am going to do, I am going to get a clique from here. I am going to get a clique C1 prime, C2 prime, Ck prime, okay, in G prime. How do I do this? Okay, for this clique U, I take, okay, I am not going to do anything, but I am just going to replace your name with UV. I am not going to do anything with U. I am going to replace U, like this is V. I am going to replace this with UV, just naming change. And if there is an edge UV, you contract this edge and make this. Okay? Okay. Now, what happens then? Why is it true? So notice one thing, right? Look at all the edges which U was adjacent to. You know that V is also adjacent to same thing, right? So when I replace by U the vertex UV, it doesn't matter, right? Now look at any edge which is, so the only edge which is not present, look at the edges which are, look at the graph GUV. Every edge which is present in graph G is also present in the graph G prime in the following sense. Look, basically, if you had a copy of edge here, you know there are two copies of edge here. So this is just keeping only one copy, right? So whatever U covers, UV covers. So now replace UV, you can check for yourself that every edge is covered. Okay, every edge of G prime is covered by this new K cliques, where I'll look at the old K cliques and replaced every vertex U with the new vertex UV. And for the reverse direction, what will I do? I said, okay, fine. Suppose C1 prime, C2 prime, CK prime covers K edges in covers edges in G prime. So now look at C1 prime. Okay, if there is an edge UV, you uncontract yourself. You now make UV, put an edge, and just leave it. Now what you know, whatever this U is adjacent to, same V is adjacent to. So it doesn't matter. This is still a clique, right? And you know that every edge here, right, will be covered by either U or V. Okay, every edge which UV edge adjacent to, you know, both U and both V are adjacent. So if I replace UV with this, then this is good. Now this happens for every edge, so that's perfectly fine. Now, but the problem is, why do you know, why do we know UV will belong together? Because if U and V, UV doesn't belong so together, it means the only reason UV will not belong together in some clique, because, or the, I mean, that's not the right way of saying. Okay. Why do we know that the clique, that there exists a clique that contains UV, right? And this is why we have because it could be that UV becomes an isolated vertex. This is why we have the following rule, that if UV is an isolated edge, then our reduction rule is very simple. What we did, because we know that if UV is an isolated edge, they are not adjacent to any other edges, then there is the only way you can cover this clique is by taking this edge, then you just delete this edge and you decrease the parameter by 1. So this is why we have a rule, if such an edge is there, then you take G minus UV edge and K minus 1. Okay? This is why, if you notice, we have this rule, right? If UV was an isolated edge, decrease K by 1. And so if such an isolated edge do not exist, it means, what is the meaning of this? UV also has some other neighbor, common neighbor. In that case, UV also, in G prime, UV has an edge adjacent to itself. It means there will be a clique where UV will be present. And then if UV will be present, then the edge UV will be covered also in G prime, G. So this nice contraction operation preserves this. So these are like reduction rules, right? We look at the graph, we analyze its structure, and we are able to say, right? And the proof is very simple. Okay, so that's what the reduction rule. What happens? So let G comma K be an irreducible yes instance, meaning you cannot apply any of these reduction rules, and C1 to CK be its edge clique cover. Okay, and so what we do to prove that the reduction rules is sound, or reduction rule applies, is very simple. So what we say that, look, for every vertex V, let's associate a binary vector xv. So let's fix this clique C1, C2, Ck. Okay, let's fix this. And I'm going to write what is a binary vector for xv? Well, is V present in C1? Then I put 1. Is V present in C2? Answer is no, then I put 0. Is V present in Ck? Yes, then. So then you get a k-length vector which tells V is present in which all cliques. Now let's ask ourselves, if for two vector V and W, two vertices V and W, xv is equal to xw. It means, notice that V and W, they are present in the same cliques, so they see the same neighbors everywhere. So you can show that if this happens, xv equal to xw, then because they are present in the same cliques everywhere, so look at a neighbor which is a neighbor of, we will show. So look at a neighbor of y. So first of all, v and w are present together in some clique. So the edge, there is a neighbor between v and w, they are neighbored. Now look at any edge y, which any neighbor of y. Okay, so this edge vy will be covered somewhere, right, in some clique. So look at this edge, okay. But I know that w is also present there, which implies that w also has a neighbor to y, which implies that neighborhood of v is equal to neighborhood of w. So if there are more than 2 power k vertices, then implies by pigeonhole principle there exist v and w such that xv equal to xw, and if there are two vertices whose close neighborhood is same, then our reduction rule 2 would apply if G contains an edge uv with nu equal to nv, contract uv. So we found two vertices uv whose close neighborhood is same, which means not only they are open, not they have a neighbor among themselves, and all their outside neighbors are also the same, which implies that then these kind of vertices are also called twins. So all vectors xb are different, thus there are at most 2 power k of them, hence irreducible graph has at most 2 power k vertices. So what's our kernel? So we apply this kernelization reduction rule. If the number of vertices is more than 2 power k, you immediately say no, or you obtain a kernel. I think with this we will stop this lecture and we'll come back again for the next lecture. Okay.